All right. Hello, class. Thank you for tuning in today. Um, Today, what I'll be doing is the same thing as yesterday, going over a free response from AP Physics 1. Tomorrow, I'll be doing the same thing. And after that, I will be having an extended Discord session tomorrow for any last minute questions you have. So think up your last minute questions. I wanted to show you, I had that railroad tie yesterday and that I found, and I heated it up, and I'm not done with it yet, but this is what I have so far. So I probably doubled the length of it, I would say, and as you can see, it's still quite thick. It's about maybe 3/8 of an inch thick. So I'm gonna, when you hit the metal, it spreads out sideways. So I'm gonna hit the blade and try and get it to spread out. And I think I'm gonna try to get the blade to curve forward a little bit. But yeah, so I'm working on it. It was really fun. It's pretty crazy because after I took this out of the forge, it was sitting on the ground outside, and there was like a cool breeze blowing, and it literally took 30 minutes to cool down to a temperature where I could touch it. So I mean, it was like really hot, and I dropped it in the grass while it was red hot, and the grass just immediately lit on fire. So, and I'm gonna put. I have a tree in my backyard, and I've been cutting branches off it, and I'm gonna glue some of the tree branches as the handle material. So, anyways, it needs to be thinned out. It needs to have a lot of material taken off, and then it'll be my first knife construction. So, anyways, I'm pretty happy with it so far. Hello, Sebastian. Hello, Elena. Hello, Alex. Hello, Will. Hello, Ainsley. So, let's get down to the physics. Once again, I'll be skipping questions that are on. I'll be skipping questions that are about either electricity or waves, because those are not on the AP exam this year. All right. So, question 1 says, a wooden wheel of mass M consisting of a rim with spokes rolls down a ramp that makes an angle theta with the horizontal as shown. The ramp exerts a force of static friction on the wheel so that the wheel rolls without slipping. On the diagram below, draw and label the forces that act on the wheel as it rolls down the ramp. Clearly indicate at which point on the wheel each force is exerted. Draw each force as a distinct arrow starting on and pointing away from the point at which the force is exerted. So we're going to have 3 forces. We're going to have the weight force, and the weight force acts through the center of mass. Okay, which is the center of the wheel. So the weight force is right there. I'm going to move it back in a second. And then we have the normal force, which acts from the point of contact, normal to the surface. So I'm trying to draw that as a straight arrow. So that's where the normal force is. And maybe I'll make it a little bit shorter. There. So that's the normal force. And then we have friction. And friction acts parallel to the surface, opposite to the direction of motion. So that would be kind of in this direction. So I'm not labeling these forces. You would want to label them. So moving this back, we've got sort of these 3 forces. Okay. as the wheel rolls down the ramp, which force causes the change in angular velocity of the wheel with respect to the center of mass? The normal force, the answer is friction. And the reason is that torque is F times R, okay? So if we look at the weight force is acting from the center of mass. So the weight force has R equals 0. The normal force has R not equal to 0 because it acts on the edge of the wheel. But the normal force, remember, it's F perp times R. The normal force is not perpendicular. It's actually parallel to the line connecting the center of the wheel to the surface. So friction is the only force that has R not equal to 0 and F perp not equal to 0. For this ramp angle, the force of friction exerted on the wheel is less than the maximum possible static friction force. Instead, the magnitude of the force of static friction exerted on the wheel is 40% of the force, or magnitude of the force or force component directed opposite the force of friction. Derive an expression for the linear acceleration of the wheel's center of mass in terms of m, theta, and physical constants. Okay. Oh, hey, Stephen. So let's do that. So this is number 1, part B. And so if we think about the equations that are going to describe the motion of the wheel, we've got a linear Newton's second law, net force equals ma. And then we've got a rotational Newton's second law, net torque equals I alpha. Okay. The net force, going back to the free body diagram, we have weight force, friction, and normal force. The component of the weight force that acts down the incline is mg sine theta. That's the component of the weight force that acts down the incline, and we've done that with inclined plane problems. The normal force on an incline is mg cosine of theta. All right. Now notice how it said that the force of friction is 40% of the maximum friction force. So remember, the maximum static friction is mu sub s times normal, but we're at 40% of the maximum. So it's going to be mu mg cosine theta times 0.4. All right. So this is the net force on the wheel, and that equals ma. So let me simplify this a little bit by crossing out the mass. So we get g times sine theta minus 0.4 mu cosine theta equals a. All right. So then we have the rotational form of Newton's second law, and the oh, well, I think we just did it, right? There you go. That's the answer. Because it's in terms of m, theta, physical constants as appropriate. So that's the answer. Okay. Cool. So I guess we didn't need that one. Part C. In a second experiment on the same ramp, a block of ice, also with mass m, is released from rest at the same instant the wheel is released from rest at the same height. The block slides down the ramp with negligible friction. Which one would reach the bottom of the ramp with the greatest speed? The answer would be the block. Okay? And we talked about this, that the block's kinetic energy is only translational kinetic energy. Whereas because it's sliding, the wheel has translational and rotational. So if we look at the gravitational potential energy becoming kinetic energy, in the case of the block, all of that gravitational potential energy is becoming translational kinetic energy. Whereas if we look at the wheel, only some of the gravitational potential energy becomes translational. So that means that the wheel is going to have less speed. Another way you could think about it is that the wheel has friction opposing. I'm sorry about that. I'm so used to my connection being stable that I didn't even notice I was disconnected. But let me go back to that. So labeling in terms of forces, the wheel must have friction, because if there's no friction, the wheel won't roll. Okay? Man, it's breezy here. If I argue in terms of energy, the wheel has both translational and rotational energy, which means that there is less. Oh my gosh. I'm going to close the window. It's a nice breeze, but so the reasoning in terms of energy, if you have two forms of kinetic energy, you're going to have less translational kinetic energy once you get to the bottom. Okay, so we're moving on to question 2. A new kind of toy ball is advertised to bounce perfectly elastically off hard surfaces. The student suspects, however, that no collision can be perfectly elastic. Okay. The student hypothesizes that the collisions are very close to being perfectly elastic for low-speed collisions, but that they deviate more and more from being perfectly elastic as the collision speed increases. Design an experiment to test the student's hypothesis about collisions of the ball with the hard surface. Okay. So here's what I would do. This is an idea. What quantities would be measured? So I would make a graph of initial height versus final height after the bounce. Okay? Now, so basically all you would need for this is a meter stick. Right? Because all you're doing is you're measuring initial height and final height. You could use maybe some video equipment if you wanted to really be accurate about how high the final height is, because it's bouncing up and it's... So basically what I would do, it's a really simple experiment, is I would just make a data table of initial height and how high does it go after the bounce. Okay? All right, so for part B, what would the data look like? Well, if the collision is perfectly elastic, then if you drop it from height 1 meter, it's going to bounce up to 1 meter. So basically, your initial height would equal your final height. So this, you would expect the data to look like a line of slope 1. Okay. However, what I would expect to see is if it's not perfectly elastic for high speeds. Now, what would create a high-speed collision? A high-speed collision would be a collision where you're releasing it from up high. So what you might expect is that this line at first it sticks along a slope 1, but then as it becomes less and less elastic at higher and higher speeds, you would expect it to fall off the line where the final height is now less than the initial height. So I would expect something like that. Okay, so I did that. Part C says a student carries out the experiment and analysis described in parts A and B. The student immediately concludes that something went wrong with the experiment because the graph or table shows behavior that is elastic for low speeds but violates basic physics principles for high-speed collisions. Give an example of a table or graph that indicates nearly elastic behavior for low speeds but violates for high speeds. So what I would say is any graph that, again, hugs the line y equals x has a slope of 1 for low heights. And if it violates the physics principles, then I would draw something that curves up above the line, because that would indicate that basically conservation of energy is not valid, right? Because you would have, a final height greater than the initial height. So that would mean energy is somehow being added to the system. So for part 2, I would say, well, this suggests that the final energy is greater than the initial energy. All right. Question 3. Let me see. All right. A long track inclined at an angle theta to the horizontal has small speed bumps in it. The speed bumps are evenly spaced, a distance d apart as shown in the figure above. The track is actually much longer than shown, with over 100 bumps. A cart of mass m is released from rest at the top of the track. The student notices that after reaching the 40th bump, the cart's average speed no longer increases. Okay. Consider the cart's motion between bumps 41 and 44. Sketch a graph of the cart's velocity as a function of time. Okay, so in between bumps, the cart is going to pick up speed. Like this. Okay? However, once it hits a bump, the speed is going to abruptly decrease. Okay? So we're going to have a graph that kind of looks like this. So and then we'll have maybe a couple of these. So we'll have this kind of a thing going on, where the velocity abruptly decreases. Okay, now why is this showing that the average velocity is not increasing? It's because if we look at this zigzag, the zigzag doesn't go higher up as time goes on. It gets back down to where it was before Okay, so the average is just going to be something like this. It would be in the middle there. Suppose that the distance between the speed bumps is increased, but everything else stays the same. Is the maximum speed of the cart now greater than, less than, or the same as it was with the bumps closer together? So if the bumps are further apart, okay, what's going to happen is that this line is going to be allowed to continue. Okay, so now maybe it's going to look like this. All right, so let me move these out of the way. This. Okay, and then my abrupt changes. So what you can see is that if I draw the average of this, the average, because you have more time to build up speed between the bumps, the average is going to be higher up. Okay, so I would say that the maximum speed of the cart is going to be greater. With the bumps returned to their original spacing, the track is tilted to a ramp with a greater angle theta. Is the maximum speed of the cart going to be greater than, less than, or the same? It will also be greater. So what would that change? Well, if I changed the angle, then that means that the acceleration of the cart between bumps is going to be larger. So it's going to look more like this. So we're going to have, the bumps are going to be at the same locations, but the steepness of the line between the bumps is going to be bigger. Okay, so once again, we can see that if we do this, our average speed is going to be greater. Okay, so I hope that makes sense. D. Before deriving an equation for such a quantity as V average, it can be useful to come up with an equation that is intuitively expected to be true. That way the derivation can be checked later to see if it makes sense physically. A student comes up with the following equation for the cart's maximum average speed. Okay. To test the equation, the student rolls a cart down the long track with speed bumps many times in front of a motion detector. The student varies the mass m of the cart with each trial, but keeps everything else the same. The graph shown below is the student's plot for the F average as a function of time. Is this consistent with the student's equation? Well, I would say no. Why is that? Well, if we were to draw the curve of best fit, we can see that when the mass of the cart is 0, the average velocity is somewhere a little bit less than 1 meter per second. Okay? Oh, Bugger, come here. Bugger. Bugger. Come here, Bugger. We've got a little babushka Bugger today. It's a little babushka Bugger. Oh, yeah. Are you a little babushka? Yeah, here. You little babushka. Yeah, that's a very sweet boy. Yeah, you little babushka. Can I get a num-num? Thank you. Okay, go away. Okay, getting back to my lesson. Another student suggests that whether or not the data above are consistent with the equation could be incorrect for other reasons. Does the equation make physical sense? I would say that the answer is no. Okay, because we can see that D is in the denominator. D is the spacing between the bumps. I think it is. Yeah, D is the spacing between the bumps. So we can see that as the spacing between the bumps goes up, as D, the average velocity decreases. Okay? So see how D is in the denominator. So it shows that the average velocity decreases. But that cannot be the case. Right? Because if it has more spacing between the bumps, it's going to be able to pick up more speed. Okay? So that's what I would say. All right, question 4 is about circuits. So I'm going to skip it. And question 5 is about waves. So I'm going to skip it because circuits and waves are not on the AP exam this year. So that concludes the free response for today. I'll have one more free response for you tomorrow. And then you guys will be taking the AP exam on Thursday. So thank you for watching, and I'll see you tomorrow. Bye now.